Welcome back to the class. In this lesson, we're going to talk about Lagrange multiply method. Remember, this module is all about optimization. In last lesson, we reviewed and generalized a few concepts. For example, we learned gradient, Jacobian matrix, Hessian matrix, and those three concepts help us to extend the Taylor series into multivariable functions. In this hour, if you have taken the multivariable calculus, you're going to see most of the content you learned, but we're going to look from a little different perspective. We'll talk about Lagrange multiply method or any optimization. You will see the applications almost everywhere, from science, engineering, business, economics, even political science. This lesson, we're going to focus on the concepts of objective function and constraints. And first, we're going to look at the optimization without any constraint. And then we're going to look about the optimization with a single constraint equation. And at last, we're going to look for the optimization with the multiple constraints. So back to the simplest example. If I have an objective function, as you see from this picture, the height is what we'll try to maximize. Then you can clearly visualize that red point. Let me change the color. That tip point is the highest point, the peak. You have a few other small peaks down here, and then you have a valley under here on the bottom. Well, if you try to get a tangent plane, and you will find the one thing in common. They all share the vertical, or say horizontal tangent plane. In another word, the normal vectors are 0, 0, 1. And if you look from the gradient, and actually, this is 1. The gradient to x and to y are both 0. If I write the function as z equal fxy as a two-dimensional plane, you really find that this delta z, delta x equals 0, delta z, delta y equals 0. So this is where you have the maximum and the minimum. So this is our simplest case. You just visualize the height. Well, next, we're going to look at our baseline local behavior. When I call it a baseline, I mean you look at the more complicated surface. If you look at each of those peaks locally, they really share the similarity of this paraboloid, which is the equation given here in the item A. On the other hand, you can put it upside down when you put the negative, and then I can sketch the graph like this. Let me change the color. And again, it's a parabola, circular. That's the shape. And then at this point at the origin, you get the maximum. Oh, this is the maximum. I'm sorry, this is the case B. And what I try to draw is the minimum. In the case like this. So that point orange is the minimum. So the first two cases are exactly the opposite because the orientation is upside down. One in here, for the case B, we got the maximum, and what you could look at here. And the case A, we got the minimum. What about the third case? Z equal x squared minus y squared. Well, another way to look at this surface, you can write it as x times y. It's a good exercise for you to turn this coordinate 45 degrees for the xy, and then you remember all you need is to multiply the rotation matrix. You're going to find an equation z equal x squared minus y squared, or z equal 2xy, the real difference by a rotation. They represent the same surface under different coordinate rotation. In other words, I'm talking about this surface and this surface have the same shape. We call it a saddle surface. And then you have a saddle point right here. You can look at this point, goes down, and this is from the one side of the horseback to the other side of the horseback. You can imagine. And the other curve going down this way, you can think it's from the head of the horse to the back of the horse. So different from the previous two examples, the middle point, it's a maximum to the red curve and the minimum to the green curve. Then put it together, it's neither minimum nor maximum of the surface. It really depends on what direction you are moving forward. So the three examples I gave to you here, I call it three baseline, x squared plus y squared, that behave is like a minimum. Negative x squared minus y squared is maximum, and the x squared minus y squared equivalent to the x times y if you do a rotation, and it's a saddle point. So what are in common? Well, what in common is if you look at the three gradient, let me call it F1, the gradient here, for the A at 0, 0 at the origin, it's going to be 2x, 2y, put 0, 0, you know it's going to be 0, 0. And so it's this one, the same thing, is 0, 0. If you take that derivative, 2x is y, 2y is x, at the origin for the D is also going to be 0, 0. So they are all considered at the critical points, but the one is the maximum, one is the minimum, one is nothing. That's called the three baseline. We learned from last lesson, if you want to get the maximum and minimum, you have to be at the critical point. And the gradient has to be 0. But what is the sufficient condition? Let's look at the behave from the point of Taylor series. And we look at the local behave. Any surface, even like the first one, like this complicated surface, locally you can always expand as a Taylor series will look like this. And we learned this in last lesson. That's the two variable Taylor series. Let's check every term to see if you remember. The first one is the height of the surface, because I have only two variables, x and y, f, that's a surface. The second one represents the tangential plane, the tangent plane, you can call it. The third component, you got this quadratic term, x minus x0 squared, x times y, and y squared. So this second term is the quadratic term. So if you try to put all the surface together, and this is the tangent plane, and the second is a quadratic surface, it must be one of these three types of surface. So local behave, if you look close enough to the point P0, or in another word, the x is not far away from x0, y is not far away from the y0. You look closer, and the behave of this quadratic term must be one of the three baseline. So how do you know which is which? It's like the maximum, is the minimum, or is the saddle surface? Which one? Well, the second derivative of this function, we call it Hessian matrix, you remember that, will tell you which one it belongs to. And actually, it's about the Hessian determinant. It's not the Hessian matrix. What tell you is this determinant of the Hessian. So look at this determinant. If it's positive at the point P0, that will be either maximum or minimum. If this determinant at the point P0 is negative, that will be a saddle surface. But if this determinant, I just skipped this, is 0, we don't know. I'll call it undeterminate. That's why it's called a determinant.